I will be discussing on this ab initio molecular dynamics. So in chemistry, we deal with atoms and molecules. So to understand the behavior of these atoms, how they interact, how they move, is very useful for us. So one approach to understand this behavior is to do this molecular dynamics simulation. In the molecular dynamics simulation, we integrate the equation of motion, and these equation of motion require the force interacting on each atom at each time step. So the idea to calculate this force in molecular dynamics is that we can use a predefined potential energy surface, and then we can simulate our system on that surface. But constructing a potential energy surface is not an easy task. Now, suppose we have we have a system with 2 degrees of freedom, and so this is the 1 degree of freedom, this is the 2nd degree of freedom. Now, suppose we want to calculate 10 points on each degree of freedom, so we have to calculate 100 points. So we have to do the calculation for 100 points for these 2 degrees of freedom. But for realistic system, we have 3n minus 6 degrees of freedom. Now, and here n is the number of atoms. So if we want to construct this potential energy surface, we have to calculate total 10 to the power 3n. We have to done the calculation at total 10 to the power 3n number of points, which is computationally very costly. So the idea of molecular dynamics is to reduce the potential up to pairwise interaction potential up to two-body system. So this is the empirical form of the potential which we use in this molecular dynamics simulation. And we can, so, okay. The total potential of system is around n factorial by 2, where n is the number of atoms. And this pairwise is around, so it reduces the efficiency and it make the simulation fast. So we can calculate this potential energy surface more efficiently. So we can simulate a large system for longer time scale using molecular dynamics simulation. It is very useful, but there are some limitations using this approach. The first one is that it integrates out the electronic degree of freedom. So there is no information about this bonding, changing of pattern of bonding, like bond forming or bond breaking. And system like ecosystem, where the many body effect can be important, many body effects such as in two-body system, like we have this water system, and we want to capture the interaction between these two hydrogen atoms. So up to two-body system, we are calculating only so our interaction depend only on these two atoms. This one, this electrostatic potential and this Lennard charge. So we are not capturing the effect of this neighbor atom. So what is the effect of these atom on this lone pair on this hydrogen atom and this hydrogen atom? So these are the many body effects. And third one is different type of atoms, means the different type of interatomic interaction that have to be parameterized. So in this empirical force field, we use these parameters. These are different for different atoms. Now, suppose if we have a system with large number of atoms, then we have to parameterize a large number of parameters. So these are the few limitations of this molecular dynamics simulation. So to overcome these limitations and improve the accuracy of our system, people use this ab initio molecular dynamics. So the basic idea of this molecular dynamics, ab initio molecular dynamics simulation, is that we propagate our nucleus classically, and then we calculate force acting on the nucleus using electronic structure method on the fly, means at each time step. So In this talk, I will discuss all the three approaches of this molecular dynamics and what are the limitation and advantage of these approaches. So there are three approaches of this AIMD simulation. This first one is Born-Oppenheimer molecular dynamics, Ehrenfest molecular dynamics, and Karp-Renal molecular dynamics. So I will start with theoretical foundation. And first, so this is the time-dependent Schrodinger equation. This is our wave function, and this is the total Hamiltonian. So this is the nuclear kinetic energy part. This is electronic kinetic energy part. This is electron repulsion. This is nucleus electron attraction, and this is the nucleus repulsion. So this is the final form of our Hamiltonian. This is the nuclear kinetic energy. This is the electronic Hamiltonian. So this is our Hamiltonian, and this is our time-dependent Schrodinger equation. Now our goal is to drive molecular dynamic simulation of classical point particle, starting from quantum mechanical wave equation for both electron and nucleus. So there are two methods to do that. The first method is like kind of more general. In this method, we will consider the electronic part of Hamiltonian for fixed nucleus, and then we will solve the exact time-independent Schrodinger equation for each electronic state. So this is the electronic part of Hamiltonian, and this is our electronic wave function for one state. This is the energy of that state, and this is again the wave function. So these solutions are orthonormal, and our total wave function is this. So in this wave function, our electronic wave function is time independent, and this nuclear wave function is time dependent. So this is the wave function given by Born in 1951. Now, if we put this equation 8 into this time dependent Schrodinger equation and multiply from the left by the psi k star and integrate over all the electronic coordinates, we will get an equation like this. So this CKL is known adiabatic coupling operator, which will look like this. So first we will use the adiabatic approximation. In adiabatic approximation, all the off diagonal term will be 0. Why? Because adiabatic approximation says that the energy gap between two electronic states is significantly large. So there will be no coupling between two energy states. So we can ignore all this cross coupling term, and we will left only this diagonal term. Also, this term, this right term, this will also be 0. Can anybody tell me why this will be 0 for diagonal term? Hello, am I audible?
Yeah, you are audible.
Yeah. So can anybody tell me why this term will be 0 for diagonal term? Okay, so the derivative of wave function will be orthogonal to the wave function, so it will be 0. Okay, so we will left only with this term. So we can say that the motion of nuclei proceed without changing the quantum state k of electronic subsystem during the evolution. Basically, we left only with one state. There is no other state. So we are calculating, we are solving this our Schrodinger equation only for one step at a time. So we can also simplify our wave function, which was the sum over all the state, just up to single electronic state. And we can further simplify this equation by taking this term as 0. Why? Because this, according to this Born-Oppenheimer approximation, this electronic this Hamiltonian does not depend on the nuclear coordinate, so it is basically fixed. So we can neglect this term. So we will left with this equation, and this is the Born-Oppenheimer approximation. So our goal is to approximate the nucleus as a classical point particle, so we can get our this Newton's equation of motion, and we can simulate our system. So how we will do it? So I will be using this very famous semi-classical approximation. So in semi-classical approximation, we will rewrite our nuclear wave function as the product of amplitude and the phase factor. This amplitude depends on the spatial part, and this phase factor is nothing but the action, which is the integration of Lagrangian. So if we will put this equation 16 into equation 15 and solve this equation and separate the real and imaginary part, we will obtain these two equations. So first I will solve this equation 23. So in this equation, if we will multiply the equation by 2k from the left side, so it is like, so it will be like something, and similarly this part. So we will get an equation like this, and this ak square is nothing but this ik square, because this will be minus sk multiply plus sk, so it will cancel out. So basically a square is equal to psi k. So this is very famous equation. What is the name of equation, if someone knows? Okay, this is the continuity equation. So continuity equation basically suggests that the probability density of nuclear is conserved. So what does it mean? It means that the probability of finding a nucleus at each point is constant throughout the time, which is basically what classical mechanics says. So it means our approximation is in well agreement with the classical mechanics. Now I will solve this equation 22. So this is our equation, and in classical limit, this reduce Planck constant tend to 0. And if we will put h is equal to 0 in this equation, we will get equation like this. And this is the equation which is isomorphic to this Hamiltonian Jacobi equation, which is this equation. And this Hamiltonian is kinetic energy and potential energy. So if we transform this kinetic energy is, so this will be our momentum, and this will be our potential energy. So the Newton equation of motion of this for this Hamiltonian Jacobi equation is this. So this will be our Newton's equation of motion, which we have to solve for this Born-Oppenheimer molecular dynamics. And as we are using the Born-Oppenheimer approximation, so this is called Born-Oppenheimer molecular dynamics. So now I will. So what will be the Newton's equation of motion for ground state in Born-Oppenheimer? This is nothing but the ground state wave function, and this is the ground state energy. So this is the minimum over wave function. And if we solve for effective one particle Hamiltonian, such as Hartree-Fock-Ponson, so we can further get, I suppose this is one electron wave function. This is our total wave function. Now, if we variationally minimize this expectation value, with some constant such as orthonormality. So if we minimize this equation, we will get equation like this. And this is nothing but the Hartree-Fock equation. So this will be our Hamiltonian, sorry, Newton equation of motion. And this will be same for quantum theory as well. So this was the first method. Now I will, which is called Born-Oppenheimer molecular dynamics. Now I will discuss the second method. So in second method,
Akshay, so what is the main message of Born-Oppenheimer molecular dynamics? Like
the main message is that this is our Newton equation. So this is our.
Yeah, leave all the equations, but just tell me the message.
Okay, this is the, so basically we are from this quantum mechanical equation for nucleus and electron, we are just doing the molecular dynamics simulation, and molecular dynamics simulation we have to do classically. So basically we are transforming this quantum mechanics to classical mechanics to do the this to integrate the equation of motion.
Okay, so where we are using the approximation?
Yeah, sorry?
Where we are using the approximation?
Here. So first, this is the approximation. We have like divided the wave function, both electronic and nucleus. Based on that, the nuclear motion is much slower compared to electrons. So we can divide these wave functions. And
okay,
here, this adiabatic approximation, where we ignore all the off-diagonal terms here, because this electronic motion does not depend on the nucleus. So the coupling, the diagonal term will be 0 as well.
Yeah. Okay. Okay. And you actually you are telling that the electron density is concept. Sorry, density is concept, and it is behaving classically. What you are saying?
Probability density concept. Yes, it is like that. The probability of nucleus finding at a certain point is constant throughout the time, which is basically what classical mechanics says.
At a certain point is constant throughout the time. How is it so?
It's like it is not spreading in all the region.
No, let's say at a particular time step, at a particular Cartesian space, coordinate space, you are saying that that point, the probability density at that coordinate space point will not change with time. You are saying this? Probability of finding the electron at a particular coordinate space point will not change with time. You are saying this?
No. Okay. Basically, it will not spread like a wave function. So it will be like this point particle. So for a point, it will be there. It will not be spread throughout the space. Maybe they both statements are not matching, but this is the what exactly I want to say.
Okay, fine.
And in this Born-Oppenheimer molecular dynamics, so this our potential, it is, so this potential we are calculating by this time independent Schrodinger equation. So by this equation. So we have to calculate this potential at each time step. So first we have to propagate this nucleus, then we will calculate our EK, this potential at each time step using this time independent Schrodinger equation.
Yes. Yes. Okay. But,
Anything else?
yeah, but some like basic computational technical doubts. Like, so at each time step, you are computing the potential function.
Mhm.
So how do you compute potential function at each time step? Like, how do you solve the time independent Schrodinger equation?
Okay, now this basically we will be using some approximations such as this Hartree-Fock or quantum, which I have discussed here.
Okay. Mm.
To basically now our goal is shifted from approximating this Newton equation of motion to this. So approximating the Schrodinger equation to solve this, using some approximation to solve the Schrodinger equation. So it can be Hartree-Fock.
One thing just not related to that discussion, that Chandra sir just called me and he told me that from 11 o'clock we have a meeting with Ravi, Avilas and me. Okay. So
11 means what?
11 means here after
3:30.
1.5 hour.
Okay.
Okay. So
Sorry, 2:30. Yeah.
for Ravi and Avilas. Okay. Okay.
Okay, Vansi.
And okay, that discussion, the continuity equation. Continuity equation means that the density is not created or destroyed.
So
Is-
over a
is
region, it
density.
is constant, it is constant. So if you define a region, then the
Incompressible. Density is incompressible. It
incoming
cannot be.
outgoing densities will be equal to the incoming density, like flux equal to the outgoing density.
It will be constant with incoming.
Yeah, incompressible fluid like.
Okay, fine. Nox, we can discuss later, then we can go ahead.
And regarding that unsage of this wave function, just starting from this semi-classical unsage. Yeah.
This one.
This is phase factor and
This is amplitude.
I have seen this unsage before also, means in many aspects, but could you tell us more regarding these the phase and this amplitude factor? Could you tell us more? Means why, means how one just take this kind of unsage? All are complex. A is complex, S is complex. So yeah.
I think someone from the Sri Research Lab work on this semi-classical approximation. So maybe in future he can explain this semi-classical. So I know that much. So that is what I explained.
One is phase factor, and this phase
SK
factor is most related to, later you have shown. This phase factor is related to, go down to the Hamilton-Jacobi equation.
Yes.
Yeah, this phase factor is related to action.
Phase factor not related to action, it is the action.
It is action, yeah.
It is the action, yes.
In that limit, it is action. So
yes, it is the integration of this Lagrangian.
Yeah. S is action. So, and what is the then is, can we understand this? Is the quantum?
A is the related to the probability density.
Okay.
So A is basically related to the original probability density. Okay, A is the amplitude.
Yeah. Is the amplitude? Is the amplitude?
Yeah. So it is related to density.
So if we go to that equation, Hamilton-Jacobi equation, there is no A. Okay. So A comes only with when the quantum mechanical effect is prominent. Means I want to
Actually,
understand physically.
we are separating this real part and the imaginary part. So it is only in the real part. Oh, only sorry, in the imaginary part. And in this case, it will be in this right side. But in classical limit, we are taking this reduced Planck constant as 0. So this term will be 0. So yes, this Hamiltonian Jacobi does not depend on A.
Yes, Hamiltonian Jacobi is the pure classical form. That's why as the
sorry, the isomorphic equation. That's why that is the it is the isomorphic.
Yes, so Hamiltonian Jacobi equation is the classical form. That's why it is related to the only action quantity. And the main motivation of choosing the answers is that we know that each wave function is in general is a complex quantity. So to connect with classical things, so semi-classically we choose any wave function is a combination of amplitude and phase. Okay, so amplitude is complex quantity in general. So A times phase factor is exponential I times some quantity. Now, how do you choose some quantity? S. So the classical mechanically, so the main connection with the quantum and classical is the S quantity. So that's why we choose the action value. So that's the connection between the semi-classical and the quantum thing.
Okay. Maybe means we can understand more in terms of if we connect this thing in path integral.
Yes, it is the form, identical formulation.
Okay. And this is in the second equation, there is no H cross part, means in the imaginary.
Yeah,
So,
no.
So there is no correspondence. So there is a inherent relation between these dependence between SK and AK. Means this kind of inherent dependence in some places like Kramer's chronic, means this is a different thing also, but but this kind of inherent dependence is there. And so could you comment anything, or they are just means it does not depends in which limit you are
classical limit
you are observing. Yeah. Means there will be in the classical limit also there will be same depend. This equation, this kind of dependency will holds. Means AK means probability amplitude will be related to this phase factor.
No, probability amplitude will be independent to the phase factor.
But no, this is independent, directly independent, functionally independent.
Yeah.
But they can be transformed, like they are related in this equation, through this equation 23. Just like means in Kamarskoni also, means those are very two independent thing, but in Kamarskoni also imaginary part is related to the real part, but
yes.
Imaginary related and real part are not dependent with each other. They are independent things. So there is a reason for that why those are related, but here
actually that is why I was suggesting that we can have a detailed discussion on this semi-classical approach. Or there are other approximation as well. So we can have a detailed discussion in future about this methods.
Okay. Yeah, you can.
Should I proceed?
Yeah, you can.
So the second method is a bit different. Like in this method, we are maintaining the time evolution of the electrons. So we are not considering electrons as time independent. So in this approach, this is our ansatz, and this is our electronic wave function, which is also dependent on time. This is the nuclear wave function, and this is some phase factor which is introduced to make the final equation more simpler. So this is our E energy, which is average over this electronic and nuclear wave function, and H is the electronic Hamiltonian. Now, if we insert this equation 29 into time-dependent Schrodinger equation, multiply from the left with the psi star, chi star, and integrate over both the electronic and nuclear coordinate, we will get these two equations. So this first will describe the motion of electrons, and the second will describe the motion of nucleus. And also both these wave functions are orthonormal. So these equations are the time-dependent Schrodinger, the time-dependent self-consistent field method, which is given by Dirac in 1930. And in these equations, both electrons and nucleus move quantum mechanically in a time-dependent effective potential. This is this potential. And this potential obtained from the average over the other class of degree of freedom. Like in case of this electron, this is over the nuclear coordinates, and in case of nucleus, this is over the electrons. So we will use the same approximation, same semi-classical approximation in these equation as well. So this is this nucleus wave function. We will use again the same method, and we insert this equation 34 into this equation, and we will get equation like this. This is again the same continuity equation, and we will do the same thing here. This H cross will be 0 in classical limit, so we will get equation like this. So this is again same isomorphic to this Hamiltonian Jacobi, but now the output is this. So this will be our equation of motion, but there is still one problem. So this potential we have to calculate using this electronic wave function, and if we look at this equation, this electronic wave function is still dependent on the wave function of nucleus. So now we have to because nucleus is not a quantum particle anymore, so we have to transform our nuclear wave function, this probability. This is in classical limit, so that we can have our nucleus as a classical point particle. So yes. So this will be our final equation to solve solve the phi, and this will be what our equation of motion. But now the phi we will solve from here, and there is no quantum dependent. There is no dependent of this wave function on nuclear wave function on this phi. So now this is classical, so we can use it. So this will be this is given by Ehrenfest. So this is the Ehrenfest molecular dynamics. This was our second approach. Any question from you?
Yes. So what is the difference? Like I cannot understand the.
So basically,
So there are too many.
so basically, yeah. So in that approach, we considered the electron fixed and we propagated the nucleus. Now we are evaluating the dynamics for both electrons and nucleus here. Now our wave function of this electrons and nucleus, both time dependent. So basically we have to minimize the wave function initially, and then we will propagate our wave electron wave function. So we don't have to do this time independent Schrodinger equation to calculate this energy of state. And also, so in the other approach, this Born-Oppenheimer molecular dynamics approach, we were using this adiabatic approximation. So basically it suggests that there is no coupling between two states, but here the coupling is allowed.
Okay.
So if we relook at both Ehrenfest and Born-Oppenheimer molecular dynamics, so as Oppenheimer, this Ehrenfest molecular dynamics is evaluating the electrons as well. So our time step, the integration time step, which we are using to integrate this equation of motion, must be small so that it can capture the electronic motion. So it will be somewhere in the range of 10 to the power minus 5 femtosecond. In Born-Oppenheimer approach, so this is, we are using time independent Schrodinger equation and no electrons dynamic whatsoever. So it means we can use the large time step as well. So sorry, 1 femtosecond. And this is again, we have to minimize electronic wave function only initially, then we will propagate our wave function. But in this case, we have to calculate, we have to minimize our wave function at each time step. So we have to calculate we have to do this time independent Schrodinger equation calculation at each time step. So these two methods have some limitation and some advantage. So the best thing one can do is that use last time step, because if we will use 10 to the power minus 2 femtosecond, it will be like too much low. So if we will simulate like in nanosecond, then you can figure out how many number of steps we have to do. So in an ideal scenario, we should have a last time step, and we should also avoid this time independent Schrodinger equation calculation at each time step. And also we should capture all the electron dynamics. So this is what actually Carr and Perinello proposed in 1985. So this is our third method, which is this Carr-Perinello molecular dynamics. So they have taken, in this approach, they have taken the advantage of both these methods. So this is basically based on the idea that the idea is this adiabatic separation between the fast electronic and slow nuclear motion. So they propose this Lagrangian. Here, this is the kinetic energy part of nucleus. This is for electron. This is the potential, which is average over this electronic wave function. And this is some constant, such as the orbital orthonormality. So this is some fictitious mass. And now in classical mechanics, the force on the nucleus is obtained from the derivative of suitable Lagrangian with respect to nuclear position. So this suggests that a functional derivative with respect to orbitals, which are interpreted as classical fields, might yield like correct force on the orbitals given a suitably defined Lagrangian. So the corresponding this Newtonian equations of motion are obtained by this Euler-Lagrange equation. So this is for nuclear position, this is for orbitals. Now, if we look at the equation of motion in this Carr-Perinello approach, so this is for the nucleus and this is for the electrons. These constants are again like some orthonormality constants. And if we look for the specific case such as quantum theory, so this will be our final Lagrangian for CPMD. And this will be the equation of motion. So the this nucleus evolve in a time at a certain physical temperature, which is directly proportional to this kinetic energy of nucleus. And these electrons have a fictitious temperature, which is directly proportional to the electronic kinetic energy. Now, many of you here have here like cold electrons. So what is the meaning of cold electron? Cold electrons means that the electronic subsystem is close to its instantaneous minimum energy. Basically, it is close to exact Oppenheimer surface. You are getting this point. Okay, so the remaining task is to separate this nuclear and electronic motion such that the fast electronic subsystem stay cold for long time, but also follow the slow nuclear motion adiabatically. So this is possible if the power spectra for both the dynamics do not overlap. So basically, there should not be energy transfer between the hot nuclei and the cold electron. So how it is possible and why it is possible? So this is the dynamics generated by this Carr-Perinello Lagrangian. This is the Fourier transform of this equation, basically velocity autocorrelation of electrons. And this triangle, this is the highest frequency for the nuclear phonons. So we can see there is a separation between both these modes. So the highest frequency of this nuclear phonons around 100 to 105 centimeter. So there is separation between, so there will be no energy transfer. So this was the first approach. And this is for the two silicon atom on the periodic diamond lattice using LD approximation on quantum theory and using time step of 0.3 femtosecond and this fictitious mass around 300 atomic units. But this is in practice, it can work. But will it work in paper? It can work, but will it work on practice? So just like the energy, the total energy should conserve according to classical dynamics. So this is our total energy, and it is plotted for this system, and you can see that it is conserved. And this is the kinetic energy of the electron. So here, yeah, it suggests that in this plot, so there is a bound oscillation around a constant value. So it means that electron do not heat up in the presence of hot nucleus. So it will oscillate around the same constant value. And also, given this separation, the stability of the propagation means basically are the force acting on the nucleus are actually correct in CPMD. So this is the comparison between the force from CPMD and the Born-Oppenheimer molecular dynamics of the same system. So this dotted line is from Born-Oppenheimer molecular dynamics and this solid line is from CPMD. So it is also in the well agreement. So we can say that the force acting on the nuclei is correct for CPMD as well. Now the question is how to control the adiabaticity. So as I suggested previously that this gap between the minimum energy of the electron, the minimum frequency of the electron and the maximum frequency of phonon should be large enough so that there will be no coupling between both. So this is our minimum frequency for electron, and this electron gap is the energy difference between LUMO and the HOMO. So this highest frequency of nucleus and the lowest frequency of electron, both are the physical parameters. So we cannot control this parameter. The thing we can control is the fictitious mass, this to minimize, to make it less or more. So this is what called adiabaticity parameter. But like to increase the separation, we can increase the fictitious mass. But there is one thing that limit the, so we cannot just adiabatically decrease this fictitious mass, because this is our this highest frequency of the electrons, and this E cut is the kinetic energy of this electron. So this time step of integration is directly dependent on the fictitious mass. So if we will increase or decrease this fictitious mass, then our time step will be very low. So we will have the same problem that we cannot simulate our system for large time step. So it is like trade-off between fictitious mass and the time step. If here, if fictitious mass is too small, then electrons are too light. Basically, electron motion will be slow and it will couple with nuclear motion. So it will give some error in the simulation. And if fictitious mass is too large, then time step will be too large, then it will neglect the electrons motion. So this was the CPMD. Now, which method to choose? So maximum time step is this Born-Oppenheimer molecular dynamics is around 1 femtosecond. In CPMD is around 0.1 femtosecond or somewhere there, around 1 atomic unit. So, but CPMD is more stable compared to this Born-Oppenheimer molecular dynamics for liquid system. And also more efficient, because in Born-Oppenheimer molecular dynamics, we have to solve the time-independent Schrodinger equation at each time step. So it is also computationally very expensive. But for solid, this Born-Oppenheimer molecular dynamics is preferred, because if the energy gap between LUMO and HOMO is low, then we have to decrease our this fictitious mass. But if we will decrease our fictitious mass too much, then we will lose the adiabaticity. So in case of solid, Born-Oppenheimer molecular dynamics is more preferable. And yes, one should be careful with the choice of mu, because it can affect the accuracy of the simulation. Yes, any question?
Yeah, Akshay.
Yes.
So computationally costly is one thing, but you said CPMD is more stable and efficient.
Yes. Efficient means computationally efficient. Stable, basically, it was calculated for both the, basically the energy is constant throughout. So if we use like around 500 atomic unit fictitious mass for water, and time step of around like 0.24, around 1 atomic unit, so the energy conservation limit will be around 10 point minus 6 atomic unit or million electron volt. But the conservation unit for the conservation between energy in the Born-Oppenheimer molecular dynamics is much higher. Basically, the fluctuation of energy in Born-Oppenheimer molecular dynamics is higher compared to CPMD.
That part, that BOMD, we already ensure that it is always in that Born-Oppenheimer surface. So Yeah, stability means in which respect?
Stability basically the conservation of energy throughout the simulation.
Uh, Conservation
Actually,
BOMD is like your classical MD.
just like
Force is
classical MD.
calculated is from this. Force is calculated from electronic structure calculation.
Mhm.
So their conservation is much more, I think, much more stable compared to CPMD. CPMD, they are.
But it is also depend on the time step of Born-Oppenheimer molecular dynamics.
Yeah, time step. Yeah, it is also depend. But yeah, if we choose that your 1 femtosecond typical DT time step for means it is if we choose much smaller than the vibrational means highest frequency degrees of freedom. So then how could we compare? Means this statement more stable
Mhm.
is not so clear. And
Actually,
also
there is a table in this Dominic Marks and George editor book. So
okay.
in this, they have mentioned few things like time step for both CPMD and Born-Oppenheimer molecular dynamics, conservation of energy in atomic unit, conservation per unit time, and the time taken by the simulation. So this Born-Oppenheimer, this BOMD conservation for time step 10 atomic unit is around 10 to the power minus 6 per picosecond.
Okay.
And the computational cost is 16,590 seconds. And for the same time step, 10 atomic units in CPMD, the conservation is around 10 to the power minus 7 atomic unit per picosecond. So it is 1 order less. And the time taken is only 1600 seconds. So
For
it
same
is one
time step?
for same time step.
Time step is time steps would be
10
much,
atomic unit.
much smaller. Just here you have shown.
So this is for this system. This is, I think, for the silica system, I guess. They have also compared this 32 water molecules.
Okay, but yeah, means in CPMD they means.
And CPMD is also stable because it is taking this electron dynamical part into consideration.
Yeah,
but in Born-Oppenheimer molecular dynamics, the electronic contribution is only calculated at a certain time. So
yeah,
it is also
electronic,
more.
yeah, that we can understand like this means there is no that electronic degrees of.
But if if we just as you were saying that this Born-Oppenheimer is always stay on this Born-Oppenheimer surface. So yes, if we use this fictitious mass too large, then it will deviate from this surface. So
yeah, it will deviate from this surface.
Yes,
and
yes.
it
So
will oscillate.
energy.
CPMD,
Yes.
The energy will oscillate around this Born-Oppenheimer surface. And yeah, it oscillation is large if we choose the mass very large.
So the choice for this fictitious mass is very important for both time step and accuracy.
Now, given that our recent computational means the algorithmic trick that Born-Oppenheimer and CPMD, if you run both are take almost similar time. Means this efficiency, computational efficiency was there at the initial times when those things are developed. Now, actually, that's why nobody used this CPMD, normal CPMD. They used this second generation. This is another topic. So, and also this RN-fast molecular dynamics.
It is too slow.
Yeah. Why means I want to understand means in CPMD we can understand in terms of density function formalism. Okay, density, electron density formalism. But RN-phased molecular dynamics, where both the things are coupled, Carpinello molecular dynamics, both the things are coupled, but here this electronic
But there is a
part
separation
somewhat,
between most.
here electronic part is we don't directly couple with the electronic orbital. Okay, here electronic part is somewhat blurred. We just maintain the constraint. Okay, constraint is our known in the CPMD, and constraint is related to this orbital, electronic orbital phi. So to to define we define the Lagrangian, means there is a constant which depends on phi. So we define a Lagrangian which also depends on phi dot, like kinetic energy component. In RN-phased molecular dynamics, there is actual orbital, electronic orbital in RN-phased molecular dynamics. Means there could we means also formalize this thing in terms of density matrix? Electron density, that
density matrix.
Yeah, just like means in BOMD, CPMD, that's why means for BOMD also we can means there are similar electronic structure theory. We
Just
can
like
okay, so,
we can actually formalize
yeah.
in
But RN-phased, I don't know.
In RN-phased we can also like we can also convert this RN-phased into Born-Oppenheimer molecular dynamics. And suppose this is our
not converting, but I want to use those density functions.
We can use that.
On some,
yes, we can use it.
Go to that RN-phased part.
This is the RN-phased.
Okay.
We can just use this psi as 1 electron, this H as 1 electron, this wave function, or this Hamiltonian effective 1 electron wave function, and psi is this determinant of this 1 electron wave function, this orbital wave function.
Okay.
This formalism is very old, but actually the first AIMD simulation was done in 1991, and this RN-phased formalism was given in like 1930, and this Born-Oppenheimer molecular dynamics, this formalism given in 1956, something like that. And first this simulation of liquid system was done somewhere around 2001 or like that. So this is very new. This is actually, this come into practice after this Ponsam theory.
Here, effective potential VRIT means in Born-Oppenheimer it is clear we have to solve it means with respect to minimum. Then now here
so this is
we have a mini electron Hamiltonian.
Yeah, this is
then means in terms of computation I am thinking.
This is our potential, which we have to solve
where
using
psi
this.
is not the ground state.
Yes.
So
it is because it may have the coupling between each state. But now suppose
initially we have let's say we have ground state wave function.
Yes.
Okay, for electron and nucleus. So then okay,
we can actually like if we have ground state wave function initially, and suppose suppose the energy difference between ground state and excited state is too much. then this is nothing but the bone open IML molecular diameter. We can just
that is okay.
Mhm.
Yeah. Then we
Uh-huh.
can reduce that part. But I am thinking when this is really meaningful, then how can we compute? This high, go to that coupled equation part earlier. You just here. Okay. So is the electronic part. This coupled equation. Okay. This is reduced to that classical limit in the RN fist. Okay, we have to check. I think I have not seen that anybody use this RN fist MD for the real like density matrix formalism and density function theory.
We can use this ground state electronic wave function, minimize that wave function, and then we can propagate using some
In
space factor.
From
In principle,
theoretically, in
at least.
principle, we can propagate it.
But I don't know if it is. I think actually people have done this using time-dependent density functional theory. Time-dependent density.
That is different. Time-dependent density functional theory, that is different. That is not iron fist. There we optimize the wave function with respect to a time-dependent potential. Means Runge-Gross theorem. That is totally different. Okay, means we can means there are other way, means now people use that for non-adiabatic coupling between two different electronic states. This they consider some hopping rate between one level to another level and dynamically calculate this hopping rate and change the surface hopping, we call it. So this is one method. But for non-adiabatic things, there are many in one conference. Their whole conference is based on non-adiabatic things. So they are mostly focused on this isolated system. That's why they are mostly quantum chemistry. The discussion was mostly on quantum chemistry. But in molecular dynamics framework, I have not seen many methods to capture these non-adiabatic things. RN fist is one way, but yeah, how much practical it is. Okay. Are there any other questions or comments? And one more thing that you in the beginnings you told that derivative of psi is always orthogonal to psi, means derivative.
Yes, because
means if we take derivative means
yes, it is the eigenfunction of kinetic operator, not the derivative.
If we means in general way, means this is in general way. If
in general way, you can look at like it will be odd even seen. If we will,
in general way, if I think like suppose if I take momentum operator, Okay,
Mhm.
it is DDX. So
Yes.
if my wave function is a eigenfunction of my momentum operator, then we get a eigenvalue corresponding to momentum operator. So this is
Yes.
phi star DDX psi, and
Yes.
we get a momentum eigenvalue. This is not zero. So
But this is the wave function, or this is the eigenfunction of kinetic operator, not the momentum operator.
okay, that's why you have to, okay, means
Yeah.
you have to put, we should not put it in general way, means
Yeah, that's the
Okay,
reason,
gradient.
because exactly my minus I h bar del is the momentum operator, right?
Yes,
So,
yes, yes.
Yes.
So in that means if we take
Yes.
eigenfunction of this energy operator, then it is means its gradient is orthogonal with respect to
Mhm.
itself. Okay.
energy operator means ki Laplacians. Del square, no?
No, energy, energy operator means H psi.
Acha,
Hamiltonian.
Energy operator is the sum of both.
because if it is
Hamiltonian means it is also kinetic energy, means kinetic. If it is
no,
kinetic
if
energy, then also it is fine.
yeah, you said that's why I'm saying if it is del square, then it is where we also get eigenvalue.
Yes.
Yes, yes.
Okay.
Okay. Means we impose that condition that psi is here eigenfunction. Psi is here eigenfunction of this energy operator.
Kinetic.
Kinetic energy operator. Yes. Okay. Any other questions? And this is also very important topic. This from semi-classical to path integral.
Mhm.
I think one should means this. There is accent. Means this is the main isomorphism is very much there. Yes.
The semi-classical approximation
Mhm.
itself is very big and very important topic. Yes.
Means
Yeah,
how
I can discuss in the next week if someone
okay I can
who is going to present.